Welcome to the introduction on Drive Selectivity by Danfoss Drives. Drive selectivity is intended for analyzing and evaluating fuse protection selectivity coordination in electrical power distribution systems of hybrid and fully electric marine vessels. It is an add-on for Simscape electrical modeling tool, which is used in MathWorks' Simulink modeling environment. Drive selectivity contains models of Danfoss's drive products, which are used to build electrical schematics of the system for fault simulation purposes. The drive selectivity components can be used together with other Simscape electrical library components, and this way the user has a really good flexibility to implement all kinds of systems out there. Once the model is implemented, the user can trigger electrical faults in different and selected nodes of the schematic to simulate how fault currents and fuse protection selectivity are operating. In this video, we will give an overview and introduction to the content and the use of the selectivity toolbox. Let's go through installing and uninstalling procedures. I'm using here MATLAB version 2020b, and the instructions here are applicable to selectivity version 1.14. In this folder, I have the installation package as well as the user license, and the installation can be activated by double-clicking or from the right-click and install on the toolbox package. Now installation is complete, and we can see the new add-on in the add-on manager. Here the icon on the toolbar strip, and from the down arrow to the manage add-ons, and this is the place where we see the successfully installed toolbox. If I wanted to navigate into the installation folder, I can do it via the three dots here and by opening the folder. Here, in my case, I have assigned the installation folder under the C, MATLAB, and add-ons. If I wanted to uninstall the toolbox, I could do it via the manager here by choosing uninstall. If you want to carry out the uninstallation successfully, it is best to reboot the MATLAB and then do the uninstallation to ensure that all the files and folder are removed successfully. And sometimes there may be a conflict if you have some files open from the installation folder, then the MATLAB is not able to do the uninstallation successfully. Let's repeat the phases. I run the installer, and let's see how it looks like in the library browser. And I see the Drive Selectivity toolbox here as a new library in the tree. When I try to open and access any of the model and the content inside here for the first time, MATLAB opens automatically the toolbox key installation dialog, and here I'm choosing the license file, and the tool installs it automatically into the correct folder. In case of successful key installation, I see the opening banner when I open the files. Let's now take a look in the file content. I will navigate to the installation folder, and here under the folder license, this is where we just installed the license. In case of any problems with the license, please make sure that the license is actually installed properly here, and that you have a working internet connection. Let's examine the contents of the Drive Selectivity library. Let's examine the content of the Danfoss Drive product components. In this version of the selectivity, we have available the Vacon NXP products, and I have here tracked the product component models on a blank Simulink model. First, let's see inside the AFE model. The user can assign the type of the product. The drop-down menu contains both air and liquid-cooled AFE types and both 500 and 690 volt units. When you choose the inverter type, you can then assign what type of line filter is used, and the drop-down menu here includes both LCL and sine filters. In case you want to define the filter externally, it is possible to choose the no filter option. In the middle, there's the parameter for the initial DC bus voltage, and it is essential to assign it to the same level where the DC bus voltage starts in the simulation. Let's see inside the model mask of the DC-DC converter. Again, there's a list of available DC-DC converter products, and the user can choose between them. Again, the initial DC bus voltage is parameterizable, and in this case, the filter is always defined internally in the model when you choose between the available ratings. This is the content of the DC card model. The user can choose between the available product types, assign the initial DC bus voltage, and then set up the rapid current cutoff levels for the phases. When it comes to the cabling, the user can choose between the available cabling configurations for the output terminals. In this case, the inductive filter that is typically used with the DC card is defined by this parameter, and it is given in percentage out of units base values. The inverter models are used to define loads, inverter fed loads connected into the DC bus distribution system, and the user can define the rating of the inverter, the initial DC bus voltage, can choose whether to show or not the signal port, and this way to access some signals inside the model during the simulation, and then the load power can be defined, and with this last signal it is possible to define whether the load is enabled or disabled. And finally, the NFE models. There's a list of available NFE types. Again, the initial DC bus voltage can be defined, and it is possible to define whether the default AC filter is used or is it defined externally. Okay, let's take a look into the fuse models. I have here tracked 3 different types of models into the blank canvas, and basically they are fundamentally enclosing the same fuse model there, but there's a little bit of variation between the models. The one in the bottom, this is modeling a discrete fuse. The one in the middle models 2 fuses and is intended for modeling DC fuses or DC fuse pair. So the one fuse is for the DC plus pole and the second for the DC minus pole. And the one in the top models 3 fuses for 3-phase connection. Let's take a look into the parameters. The user can configure the fuse resistance, fuse nominal current, and the fuse pre-arc I2T rating per the fuse characteristic. These three parameters can be set based on the known fuse values or per the datasheet values. The last two parameters are to define the characteristic during the arcing period, which means that when the fuse element starts to melt and the fuse starts to interrupt the current through the fuse, these two parameters are the ones that define the fuse behavior in the simulation. An important detail in the system fault and fault current simulation is the impedances of the current carrying conductors. Namely, they are very important because of the magnitude of the peak fault current, and also the current in the different nodes of the circuit is dictated by the impedances between the sources and then the point of the fault. In Danfoss's toolbox, we are delivering at the moment three types of conductor models there, and these are shown in the picture here. The first one, the conductor segments within this block, these are pre-compiled conductor models, and the idea here is that the model is capable of representing different types of bus bars or cables depending on the rows of the pull-down menu here. And the idea is here that these have been specifically calculated for a certain type of bus bar arrangement or cable arrangement, and we have used here a third-party software and the field solvers there to calculate the impedances, and then the cable or the conductor model has been built using this impedance solution. The two other models here are based on mathematical equations. The first one models a two-conductor busbar system with a rectangular cross-section. So these two are intended for example, to model DC current circuits. Here the user can define the length of the bus bar and the cross-section by means of width and height of the bus bar. The fourth parameter defines the distance center to center of the two bus bars, and the last field is the material resistivity, which can be parameterized per copper or aluminum, for example. This one models a round bus bar. The user can define the length and the radius and the distance between two bus bars, which is defined as center to center. And again, the resistivity of the material can be defined. Okay, let's take a look into these models provided in the library. First, in the top, we have a DC bus multimeter block, which can be used to measure currents for plus and minus poles of the DC distribution line and the voltage between plus and minus poles. The other terminal here is the one that we consider as a input plus terminal, and the other one is the exit terminal. So the polarity of the signals is defined by the dot convention there. And this block here can be used directly to measure voltage and current signals in the DC distribution line, and it can be connected into the single line type of modeling style directly. This one models a DC switch. There's a configurable closed state resistance, and the state of the switch can be controlled from here or by an external signal. This one is a time-based DC bus fault component, and can be used to time and configure the type of the fault. Fault starting time and the duration can be parameterized using the first two user parameters. Then the fault resistance between the plus and minus poles is defined here. And the user can also define that what is the fault type modeled. It includes both pole-to-pole faults and the different type DC to ground faults. Finally, this component here can be used to split the single line style of DC line into two separate signals, which means that if we have the DC plus and minus as a single conductor or single line here, it can be split into separate plus and minus signals to extract, for example, signals from a specific node or for some specific modeling purpose. Finally, let's take a look into the report generator. I have dragged this component into the canvas from the utilities folder. If we look inside the component, we see that the user can define the project name, the author, file name, the report's title, the revision number, and the report ID. Once this information is filled and the user updates the schematic information, it prints this kind of a information field containing all the parameters and the information filled into the fields here. In addition, the user can generate a PDF file out of the single line schematic modeled, and once the simulation is completed, the user can run the Word report generation. We can have a look at that later. Let's see the inbuilt tutorial models. This is a simple model of a DC circuit with a fuse, source, cable segments, and the point of fault. The voltage source is defined as a 1000 volt DC voltage source. We are using the round bus bar components to define the current conductors. So it's a bus bar of 2 meters length, and the radius and the distance between the conductors is defined here. And there's a similar conductor segment after the fuse and before the point of fault. The fuse is defined here in this example as follows. There's a DC multimeter to measure the voltage and current, and the fault is defined at this point using the time-based DC bus fault component. So the fault starts at time of 2 milliseconds, the duration is 1 second, and the fault resistance between DC plus and minus poles is 1 ohm. It is important to note that when you build models from the scratch, each model needs to have at least one electrical reference point. And if you have a separate parts of the model, they need to have probably a separate electrical reference. If this is not configured properly, the solver will give you a warning or an error message when you start the simulation. And each part of the circuit needs to have a solver configuration block connected. In this case, we are running it with a backward Euler type of solver with a sample time of 1 microsecond per step. The electrical reference block and the solver configuration blocks can be found from the main Simscape library. Now we are ready to start the simulation, but what I actually did in the meantime, I made some customization on the signals here. So the outputs of the multimeter block, I have separate those into 3 discrete signals, so it's easier to differentiate between the current signals and the voltage signals. But now let's start the simulation. Now the simulation has been completed. Let's see the signals in this scope. The one on the top is the DC plus pole current. One in the middle is the DC minus pole current. And in the bottom, we see the voltage between plus and minus nodes at this point of the circuit. The fault was initiated at the time of 2 milliseconds. So this is the instant where the fault is being generated here. We see the fault current flowing in the circuit, and since it was a 1 ohm fault impedance and 1000 volts of source voltage, the current will be around 1000 amperes here in the plus and minus conductors. And at this point, the fuse has reached the pre-arcing I2T value and will go into the arcing period and starts to interrupt the current. And here, currents and voltages fade away, which means that the fuse has open circuited. And here, when we measure between the plus and minus poles over the fault, it will show 0 volts after the fault has cleared. Let's try out the example simulation of the DC card. In this simplified schematic, we have a DC distribution circuit with the DC card here in the middle, and on the left-hand side, we have a battery system. At this node, we are generating the fault, and on the right-hand side, we have a second battery here. So both batteries have their own DC fuses. Also, the DC cards here have their DC input fuses, and we have defined the conductor segments or the bus bars using these component models here. Here we have chosen the DC card as follows. So it's a CH64 NXP with a rating of 1500 amperes. Here, when we look into the circuit, we have defined the initial DC pulse voltage equal to 1000 volts. That applies to each converter here that we use. So it's important to have the initial state of the circuit so that it starts from the steady state. Otherwise, it may take a prolonged period of time before the simulation starts if it has to search for the initial conditions. The battery voltages have been defined so that they are starting from 1000 volts also, and the internal resistance have been defined as 60 milliohms in this example. And the same settings apply also for the right-hand side battery. The fault is defined as follows. So the fault starting time is 5 milliseconds, and the fault resistance is 1 milliohm. Let's start the simulation and then investigate the waveforms. Okay, the simulation has been completed. The color coding here in the fuse components, when it is red, it indicates that the fuse has exceeded the I2T pre-arcing limit, and it means that the fuse has started to melt. The gray background color in the DC cards means that the DC card has triggered. It means that the current has exceeded the cutoff level and the current has been seized by the activation of the DC card. Let's look at some of the waveforms. So this is the instant where the fault is being triggered. We see that the current in the plus and minus conductors reach a relatively high level until the current starts to decline here. And this is the moment where the fuse starts to open and starts to limit the current. So due to the arrangement of the circuit, we have the DC card here in the middle, which then isolates the left and right hand sides of the circuit with the individual batteries. But here on the left hand side, we expect that this fuse at least would burn due to the location of the fault. So only device capable of interrupting the current is this fuse here. In addition, from the results, we see that also this fuse is opening, so the amount energy in the DC capacitors of the DC card here, it is enough to burn the fuse as it was configured in the simulation. When we look into the fault current behavior here, we see a large peak in the fault current, and then when the fuse opens, it forces the current to zero. If we look into the current through the DC card, we see that the current starts to increase when the fault is produced there, but this is the level where the DC current cuts off the current and separates the two sides of the system here. The settings of the DC card are shown here. So these two levels here define where the current is being cut off. And the right hand side here, these fuses here remain healthy, and that is due to the activation of the DC card to isolate the left hand side, faulty left hand side from the right hand side of the circuit. Finally, let's see the most complex of the example tutorial models included. This is a schematic, still simplified, but resembling a DC power system, DC power distribution system that we may see on marine vessels. In this case, at this point, we have a three-phase AC input supply here. We can think of this as a supply from a three-phase generator or any auxiliary three-phase AC supply. At this point, we are interfacing the three-phase supply with a grid converter, which rectifies the AC voltage to DC voltage. And this part here is the actual DC-DC distribution system that we are analyzing in this example. In this case, we are using conductor segment models here from the library. So earlier we spoke about these pre-compiled conductor models, which have been solved using a third-party software, or the software was used to solve the impedances. And now in this case, we have several different loads supplied from the DC system. These are labeled here. There's a propulsion drive, a CH64 unit, then a pump drive, FI9, motor drive, and one microgrid inverter. And each have a little bit different inverter rating and to illustrate what type of components may be present in a marine vessel power system. What is more, we have two sets of batteries here. On the left hand side, the battery of this half of the system is here. So the battery has its own DC fuses, there's a DC switch, and then the cabling connection which ties the battery into the main DC distribution system here at this node. Here in the right hand side, we have the DC card, which separates the left and right hand sides of the system from each other in case of faults.
And the right hand side system here, we have made a little bit simplification here. So it only includes the battery model here, but in many cases it could be that there is a similar set of equipment also on the right hand side. But now to a little bit to lighten the simulation and the computation burden, we are mainly focusing on this left hand side system, and due to the DC card being here in between the systems or system parts, we are able to make this kind of a reduction and speed up the computation a little bit. But it is good to note that although we are using the single line style of modeling here, this circuit actually includes a huge number of electrical nodes already in the schematic there behind the graphics, and therefore it is uh, uh, it is quite typical that we want to simplify as much as possible and try to reduce the problem area so that we capture only the essentials in the model, and the other parts which are not that relevant to the short circuit behavior or to the results, we try to simplify those to the extent that we are able to perform faster with the simulations. In this example, the point of fault is assigned here before the microgrid inverter, and let's see the outcome of the simulation once we have collected the results. The simulation is completed. Let's examine the results. From the color coding of the blocks, we see that the DC card has actuated. Also, the fuse here has burned, which means that the fault that we caused at this point of the schematic was isolated and no other fuses were burned. So in this example scenario, the fuse selectivity coordination worked as designed, and only this faulty equipment was isolated from the system. Of course, we can see that the DC card has activated, which means that it observed the fault current increasing and therefore disconnected the two sides of the DC power distribution system. Let's look into the waveforms. This is the DC plus and DC minus pole current flowing into the fault. We see that the fault was triggered at time 5 milliseconds. Here we reach the peak of the fault current magnitude, and after that it starts to decline, and the fault has been cleared at around time 10 milliseconds. Let's have a look on the DC card waveforms. Based on the color coding of the blocks, we see that the DC card activated. Here we see that the current through the DC card is seized at around 6 milliseconds, and this is the peak current through the DC card. This is the voltage and current on the right-hand side of the DC power distribution system. If we zoom in the voltage, we can see that the voltage declines roughly 25 volts on the healthy side of the system. This is the battery current during the fault. This is the current through the grid converter which is the interface to the three-phase AC supply. From here, we see that the fault is cleared before a significant amount of fault current would be taken from the three-phase AC supply. Let's look at the voltages and currents in these nodes. These are the current waveforms and the current supplied from the capacitor banks of the inverter units into the fault. Therefore, we see the ringing waveform. Let's try out the report generator with this model. We have now saved the schematic into a PDF file. And this is how the result looks like. Let's launch the word report generation. And this is how the result looks like. The component information from the model is collected here, and the results are summarized as follows. This is a short collection of the results, and it can be finalized into the document.